So now we're going to discuss what we call the standard normal and z-scores. And the particular reason we need the standard normal is because we've just seen that the problem with normal curves are that they all have the exact same shape, and what makes them different are their standard deviations and means. So it becomes really hard to compare things with different standard deviations and different means. And so if you look at this particular example, if I tried to compare these two curves, it's very hard to do because I know that they're similar because they are both normal curves. So what are the similarities between each curve? They are both normal. What's different about them, though, is this one has a mean equal to 50, while this one has a mean equal to 80. This one has a standard deviation of something that is sigma equals 80 minus 20 is 60, so that's 60 divided by 6. So that has a standard deviation of 10, while this one has a standard deviation of, it's like 95 divided by 65, so that's 30. So this one has a sigma of 30 divided by 6, which is 5. So they're different because they have different standard deviations to mean. So the problem exists now. We want to try to compare these things. It's too hard to compare them like that. Well, we have a solution for this, and we have a solution that has this particular thing. So every normal curve is bell-shaped and symmetric. They are all defined by their mean, remember that it's mu, and the standard deviation, sigma. If you want to compare different distributions now, we use this single curve that always has a mean of 0 and a standard deviation of 1. This distribution is called the standard normal. And remember, the word standard just means the average. So we just have this curve called the average normal curve. In statistics, the word normal also means average, by the way. So you can think of this as being the average curve. And then every value that falls on this curve is what we call a z-score. Every value that falls on this particular curve is a z-score. And here's what happens with z-score. Z-scores measure the number of, and this is the most important part of this particular curve, they measure the number of standard deviations. A value falls below or above the mean. And so here's what happens then. Every one of these values that are going to fall in this curve, we say centered at a mean of 0. Every value is measured by standard deviations now that falls on the curve. If it falls below the mean, it's a negative z-score. If it falls above the mean, it's a positive z-score. And to calculate this, here's what we do. The z-score formula for any value is z is equal to some value x minus its mean divided by its standard deviation. And here's what happens. If the value of x is smaller than the mean, then this number right here will be negative and it'll fall to the left. If the value of x is larger than the mean, this value will be positive and it'll fall to the right. And what we can do now is we can associate area. Because remember we talked about earlier, this particular curve has an area of 1 or 100%. And we can associate area to every z-score. And so the way we do that, every z-score has an area underneath the curve that is associated with what we call a percentile. So we're going to measure these things that we call percentiles based on z-scores. Probability can be expressed as a percentile. And the percentile measures the percentage of values that fall at or below a specified value. So if you look here, here is the 50th percentile. We know it as the median. 50th percentile is the median for us. But 50% of values fall at or below, and below means to the left of that curve. Now, what we're going to do is take z-scores and we're going to find the area that is associated with those z-scores. And we can do that by using these standard normal tables, which we'll get into in the next video.